If you recall last week when we introduced EMR, we said that EMR exhibits 4 properties that are properties of waves, hence EMR must be a wave, right? One of those properties was refraction. Refraction was the bending of a wave when it went from one medium to the other. The most common example of refraction, probably at least that we can think of, is this example that you see up on the board. It's when we put a pencil or something, a stick or something into the water, it appears to bend. Why does it appear to bend? Well, it's because when the light that reflects off of the pencil that's inside the water comes out of the boundary between the water and the air, it changes speed. And as a result of that change in speed, it changes direction. Our eyes, our brains aren't smart enough to initially, instinctually, recognize that light has not always traveled in a straight line, right? If we think about it, we know that light can bend and change direction. But our instinct is always that light, whatever direction it's coming right now, it's always been going in that direction. That tricks us into thinking the pencil is bent. It tricks us into thinking this portion of the pencil is where I see it right now. Whereas really, we know that that pencil is straight and it's going straight into that water. Does that make sense? The bending of a wave, in this case specifically the bending of visible light, as it goes from the water to the air, okay, tricks us into thinking the pencil is bent. I've got an analogy to help us to understand exactly what's going on with refraction. And if you were in my Physics 20 class last year, I would have given you this same analogy, so bear with me. Okay, but this year, hopefully it's going to make a little bit more sense to you because we're going to talk about refraction in a lot more detail than we talked about last year in Physics 20. We've got a parking lot here, and we've got a swamp next to it. And there's the boundary. You can see clearly the boundary between the parking lot and the swamp. This pavement has, for whatever reason, there's soldiers marching on this pavement. So we've got a bunch of soldiers here. Here's one. Here's another one. Here we go. We got, let's say, 5 soldiers marching on this pavement. And you know what soldiers do, right? When they march in stride. So they go at the same speed, the same frequency, the same pace, right? So a couple seconds later, that row of soldiers is going to be not in the same place they are right now, but in the same place as each other. Let's draw a little line that joins these soldiers together here right now. Let's call that our wave front. This is analogous to the crest of our wave. Okay, let's fast forward. Let's say 2 seconds. 2 seconds down the road, this soldier is right here. Soldier number 1, soldier number 2, soldier number 3, soldier number 4, and where's soldier number 5? In the swamp. Soldier number 5 is in the swamp, still walking in a straight line, but not quite as far as soldiers 1 through 4. How come? Why hasn't soldier 5 traveled quite as far as soldiers 1 through 3 and 4? Can't travel as fast, right? In a swamp. It's harder to walk in swampy water than it is on the paved parking lot. So now we've got a wavefront that looks something like this. Let's fast forward 2 more seconds in time. Soldier 1, soldier 2, soldier 3, soldier 4. Soldier 4 is now going to be in the swamp as well. Soldier 4 has slowed down. Soldier 5 is still walking, plugging away, but still plugging away at that slower speed. Soldier 1, 2 seconds later, soldier 1, soldier 2. Soldier 3 has entered the swamp. Soldier 4 is still in the swamp. Soldier 5 is still in the swamp. Look what happens. As this wave, or this row of soldiers, encountered a boundary between 2 media, between 2 different materials, fundamentally, what changed? Like fundamentally, what was the first thing that changed when these soldiers walked into the swamp? The speed, right? So as a result of going from one medium to the other, the speed changed. In this case, because we were going from pavement to swamp, the soldiers slowed down. If we went the other way around, the soldiers would speed up. The speed changed. Now, that change in speed, which is caused by the change in medium, that change in speed causes 2 more things to change. One, the direction. This was the direction of the wave front. Now, this is the direction of the wave front. So when a wave goes from one medium to another, the speed will change. And as a result of the speed changing, the direction will also change. What's the other thing that changes? Isaac? Good, the wavelength. Look at the wavelength here. Okay, before these soldiers have entered the swamp. Look at the wavelength here, after the soldiers have entered the swamp. Fundamentally, what changes when you go from one medium to the other? The speed. It either increases or decreases. As a result of that speed change, the direction will change and the wavelength will also change. That's refraction. The bending of a wave due to the change in speed when a wave goes from one medium to another. That's a property of waves. It's exhibited by EMR, which means that EMR must be a wave. We know that it's exhibited by EMR because that's exactly what's happening right there. When the wave went from the water to the air, it changed direction because it changed speed, and that change in direction tricked me into thinking that the pencil was bent at the surface there. So let's formally define refraction. Refraction is the bending of a wave when it passes from one medium to the other. And why does it happen? Why does it happen? It happens because of the speed change. As the speed changes, we go from medium 1 to medium 2, the direction changes, and as we saw just a minute ago, the wavelength changes as well. Now, let's try to quantify this. New term called the index of refraction, or sometimes we see it called the refractive index. The refractive index, or the index of refraction, it's a ratio. A ratio is always what? What's that? We think back to our imaginary physics thesaurus. Ratio means, another word that means the same thing as ratio is, what is it? Yeah, compare or divide. It's the ratio of the speed of light in a vacuum to the speed of light in the medium. So what we're going to do to find the index of refraction, which by the way is the symbol n, we're going to divide c, which is 3 times 10 to the 8 always, by v. v being the speed of light in the medium, whatever that is. And it will always be less than or equal to 3 times 10 to the 8 meters per second. 3 times 10 to the 8 is the biggest speed you can get. If you're in glass, light slows down quite dramatically to about 2 times 10 to the 8 meters per second. If you're in diamond, it slows down even more. If it's in ice or water, it slows down not quite as much as it slows down in glass or diamond. V will always be, at most, the speed of light in air or a vacuum, but usually lower than that. Because we're dividing speed by speed, there are no units associated with the index of refraction. It's just a number. And we said right here that the index of refraction measures how much light bends from one medium to the other. Yeah. Like it's defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. But the higher the number, the more light bends. The index of refraction of water is about 1.3. Light bends. The index of refraction of glass is about 1.5. Light bends more. The index of refraction of diamond is about 2.4. Light bends way more in diamond than it does in glass or in water, because that index of refraction is higher. Where else have we seen refraction? When you see a rainbow, that's refraction taking place. But why is it that we see the different colors of the rainbow? Why is it that we don't just see the color of the sun, right? The yellowish, whitish light coming from the sun. Well, because the water vapor in the atmosphere that causes the refraction to take place actually has a slightly different index of refraction for each different color. So, red light will refract a slightly different amount than will orange and yellow and green and blue and indigo and violet, because the water has a different index of refraction, slightly, ever so slightly, for each of those colors. Different index of refraction, different amount of bending, right? Violet has the highest, or the water has the highest index of refraction for violet, which means violet will bend the most and red will bend the least. Every material behaves that way, not just water vapor in the atmosphere. Every material has a slightly, not a lightly, that should be a slightly different index of refraction for each frequency of EMR. And that causes each frequency to bend a different amount, or each color to bend a different amount. Therefore, light splits up. It's called dispersion. We've got white light, all the colors of the rainbow together. It's like it's coming from the sun. Hits this prism. What happens when it hits this prism? Well, red light bends right here. Violet light bends more right here. So what happens when it exits and we see the screen on the other side? Well, we see a rainbow. We see the white light split up into its component colors, dispersed into its component colors. You need to know that the higher the frequency of EMR, the higher the index of refraction will be. But I'm suggesting to you that you don't remember that or memorize that. I'm suggesting to you that you just visualize that picture. How many people have ever listened to the album Pink Floyd, The Wall? Sorry? Oh, no, this is Dark Side of the Moon, isn't it? Yes. Yeah, not The Wall, Dark Side of the Moon. How many people have ever heard that? Dark Side of the Moon? The album cover is that. That's the album cover. The album cover shows red light refracting the least, violet light refracting the most. Picture the diagram. Don't memorize that violet light produces a higher index of refraction. Picture the diagram. Violet light has bent more, therefore there must be a higher index of refraction for violet than for red. Right, we said a minute ago higher frequencies disperse more than lower frequencies, but again, I'm suggesting you picture the diagram as opposed to memorizing that statement. Let me show you another place where dispersion takes place. This is the Earth. This is the sun. It's clearly not drawn to scale. The sun is way bigger than the Earth, but you're going to get the picture here, okay? There is an atmosphere surrounding the Earth. Now, that atmosphere varies in composition. The most common element in that atmosphere is nitrogen, right? But there's oxygen and a whole bunch of other elements in there as well. Sometimes there's more moisture than at other times. Sometimes there's more dust than at other times. The composition can vary quite dramatically. But the atmosphere is the atmosphere. Now, this yellow light, or we call it usually white light, coming from the sun, let's look at one ray of it, like this. When it hits the atmosphere can act as a prism, like this, like a triangular prism. And that atmosphere, with a certain index of refraction for each color, will bend each color a certain amount. But because it's slightly different index of refraction, it'll bend each color a slightly different amount. Which one bends the least? Which one? Red? Yeah, red light bends the least. So we're going to see when it gets here that red light goes like this, right? Which one bends the most? Blake? Violet. Blue, bluish, indigo, violet. So violet's going to go like this, right? All right, let's look at a person standing up here on the earth. Let's look at somebody else standing right here on the earth. What time of day is it for person number one? What time of day is it up here? Where is the sun? Like the sun is kind of on the horizon for that person, right? So what time of day is it? Yes, it's early morning or late evening. The sun is either rising or setting, right? Depending upon the composition of the atmosphere, what color is the sky oftentimes at sunrise and sunset? It's reddish, right? Because red light refracts less than other colors. It doesn't mean that we don't get other colors in there. It just means that we get a higher proportion of red light. So the sky is colored more red than other colors. What time of day is it for person two? Daytime. Where's the sun relative to person two? It's right above him, right above her. Right? Noontime-ish, right? What color is the sky? Blue, because blue light refracts more. Make sense? Now, is it just blue? No, of course not. It's not just one beam of light that's coming down here, right? There's millions of beams of light. So you're going to get other colors mixed in there as well, but you tend to get more blue than other colors, and that's why during the day the sky appears blue, and that's why in late evening or early morning the sky sometimes appears red. Make sense? Okay, that's dispersion. That's light bending at different amounts because the atmosphere would have a slightly different index of refraction for each different color. All right, let's do a tiny bit of math here and then we'll call it a day. You've got on the right-hand side of this page, don't copy this down, by the way, because on the example sheet that I handed out to you a few minutes ago, you've got that table. So there's no point in copying out that table again. You don't need to memorize any of the numbers here. There's one of those numbers, one or two of those numbers given to you on your data sheet. If you need any of the others, you'd be given them in the question. Probably buried in a page of information, not in a nice handy table like this, but it would be there. See that diamond has an index of refraction of 2.42. All the others are lower than that, which means that light bends more in diamonds than it does in a vacuum, or in air, or in glass, or anything else, really. Now, the other thing that I want to point out with this is that this is actually the index of refraction for one specific color. We're going to assume that because it doesn't vary that much, that in the context of one of these questions, it's the index of refraction for whatever light you have. So we're going to neglect that difference in index, that dispersion phenomenon that can take place. All right. Snell's law. It's just a law that provides a relationship for us. In fact, a number of relationships between the angle, between the speed in medium 1 versus medium 2, the wavelength, and then, of course, the index of refraction. Notice that theta 1 over theta 2, V1 over V2, lambda 1 over lambda 2, and N2 over N1. That means as the speed increases, the index of refraction decreases, right? V increases, theta increases, lambda increases, N decreases. That equation is on your data sheet, but don't get caught up in just blindly lambda 1 over lambda 2, V1 over V2, theta 1 over theta 2, N1 over N2. It's not N1 over N2, it's N2 over N1. You're going to use two parts of this equation, always, just two. Either these two parts, or these two parts, or these two parts, or the first part and the last part, whatever two parts seem to fit your givens the best. And that's it. Okay, let's take a look at example number 1, and I'd like to do example number 2 if we have time as well, and then we call it a day here. Calculate the speed of light in a ruby. Well, the index of refraction of a ruby is what? 1.54. So I'm going to say n is 1.54. I want to find the speed of light in the ruby. What I would suggest here is to say n is equal to c over v. 3.00 times 10 to the 8 meters per second, divided by n, 1.54. Done. That's all there is to it. Gives me 1.95 times 10 to the 8 meters per second. So clearly light is slowed down by quite a bit when it goes into the ruby. The bell's going to go, so we'll do our second example question tomorrow. What I'd like you to do tonight, and this should be very, very quick for you, is our next worksheet, which is worksheet number, no, sorry, it's not our next worksheet. We changed the order of this slightly. It's worksheet number 17. And I want you to take a look only at, right now, questions 1 and 2. They should go very, very quickly for you. Tomorrow, we'll do another example using Snell's law, and then we'll finish up that worksheet then.